October 2017 changed everything. We thought we knew extraterrestrial objects existed, but we'd never actually captured one. Robert Warwick was doing what astronomers do on every clear Maui night, scanning telescope images, searching for moving points of light against a fixed stellar background. The Pan-STARRS telescope caught something. At first glance, it looked like any ordinary space rock, drifting among our cosmic neighbors. Then the measurements started rolling in. This object was moving at 196,000 miles per hour. That's 54 miles per second. To grasp that speed with an analogy, imagine a bullet flying from New York to Los Angeles in just over a minute. That velocity told astronomers this couldn't be possible. This visitor came from beyond our solar system. No object within our solar system could possibly move that fast. Our local asteroids and comets cruise at a much more leisurely pace, averaging just a few miles per second. But this newcomer? Its speed was nearly 5 times faster, exceeding any object bound by the sun's gravity. Such velocity meant it had traversed vast interstellar space for millions, even hundreds of millions of years, before accidentally entering our solar system. We gave it a name derived from Hawaiian, fitting for this first messenger from the stars. The name means scout or messenger from afar, but its speed is only the beginning of its peculiarities. As telescopes worldwide began tracking this visitor, they discovered something perplexing. This object tumbles as it travels, spinning end over end like a cosmic soccer ball. Its brightness fluctuates dramatically, in cycles of 7.5 hours. This reveals its shape. Unlike anything we've seen in space before, most asteroids are roughly spherical, like cosmic potatoes. Most comets are irregular, yet compact, dirty snowballs. This visitor is entirely different. Truly different. The brightness variations hinted at an object over 10 times longer than it was wide. Imagine a skyscraper lying on its side, spinning through space. No known asteroid or comet within our solar system possesses such an extreme shape. The closest comparison might be a pencil in space, or perhaps an alien spacecraft, though the latter sounds too much like science fiction to be taken seriously. Yet it is there, traversing our solar system, like a fragment of metal or rock shaped by forces beyond our comprehension, as if its peculiar shape and velocity weren't astonishing enough. This visitor holds another surprise, a puzzle that has perplexed scientists for years, sparking theories, from scientifically plausible to utterly extraordinary. The mystery has only just begun to unfold, and what follows will challenge everything we thought we knew about objects from other star systems. But compared to the mysteries astronomers uncovered about its motion, the strange shape was merely a warm-up. The Panoramic Survey Telescope and Rapid Response System, perched atop Haleakala, like a cosmic lighthouse, scanning the Hawaiian skies for potential threats. Each night, this automated hunter captures images of space, searching for any points of light moving among the background stars. Most nights yield familiar suspects. Asteroids primarily within the main belt between Mars and Jupiter, moving slowly along predictable paths. Occasional comets from the outer solar system, wandering this far in, or near-Earth asteroids requiring careful scrutiny. But this October night was different. The computer flagged something that made astronomers set down their coffee and stare intently at their screens. The discovered image showed a faint speck of light traversing the star field. At first, the motion itself seemed unremarkable. Space rocks move. It's their nature. But when astronomers calculated its orbit, they realized they were witnessing something that shouldn't exist. This object wasn't orbiting our sun. It was traveling straight through our solar system, like a traveler on a highway, never looking back. When you trace its path back, it came from the direction of Vega, located within the constellation Lyra. But strangely, this object took an extraordinarily long time to reach us, approximately 300,000 years. And at that time, Vega wasn't even in that position. This visitor had been drifting through interstellar space long before modern humans walked the Earth. It drifted through cosmic emptiness, while our ancestors were still learning to craft tools and painting on cave walls. The Discovery team knew they had uncovered something unprecedented. For decades, astronomers had predicted interstellar objects should exist. Other star systems must, occasionally, flick asteroids and comets into the Milky Way, just as our own solar system does, through gravitational interactions with giant planets, capable of launching smaller bodies at escape velocity, embarking them on interstellar journeys spanning millions of years. Mathematically, these wanderers should be out there. Finding them is like searching for a specific grain of sand among all the beaches on Earth. But finding it is merely the beginning. Once telescopes worldwide begin tracking this interstellar wanderer, the real mystery begins to surface. Luminosity measurements reveal this is no ordinary space rock. The way light reflects off its surface tells a story of a journey vastly different from our own experience. This object has been severely baked and altered by cosmic radiation over billions of years. High-energy particles from supernovae and other violent cosmic events have slowly changed the color of its surface to a deep red, like rust on cosmic metal. This red hue signifies that this traveler is ancient, profoundly ancient. It has drifted through interstellar space, long before our solar system took its present form, when Earth was in its late heavy bombardment period. 4 billion years ago, under fierce asteroid impacts, this object may have already been drifting through space. Yet, even as astronomers celebrated the discovery of this first confirmed interstellar visitor, they did not know the greatest mystery still awaited unraveling. Something about this object would soon overturn every explanation they could conceive. Astronomers had never seen anything like it. What did the brightness measurements tell them about this cosmic visitor? As the object tumbled through space, telescopes tracked how its reflected light changed over time. Imagine a cosmic lighthouse beam sweeping across Earth. But this was no steady lamp. This lighthouse dramatically flickered every few hours. Its brightness fluctuated by more than 2.5 times as the object rotated. Such drastic variation meant only one possibility. This was no ordinary spherical space rock. Most asteroids are roughly spherical, like cosmic potatoes with bumps and craters. Even the most elongated asteroids in our solar system rarely exceed a length-to-width ratio of 3:1. But this interstellar wanderer is different. The brightness variations hint at an object at least 10 times longer than it is wide. Imagine a skyscraper lying on its side, tumbling through the vacuum. Such an extreme shape has some astronomers wondering if they're observing fragments of a larger object. Perhaps this elongated sliver is part of a greater structure, shattered in a cosmic collision. Millions of years ago, maybe 2 asteroids collided in another star system, and this needle-like fragment was hurled into interstellar space, propelled by that ancient impact. But other scientists propose an even stranger possibility. What if this object isn't rock at all, but ice? In the frigid depths of interstellar space, where no star's heat can reach, perhaps this visitor is composed of hydrogen ice, formed in the cores of molecular clouds between stars. The extreme cold and pressure within these cosmic nurseries can create substances unlike any found in planetary systems. The hydrogen ice theory explains its peculiar shape. As this interstellar iceberg approached our sun, its outer layers sublimated and shed, carving the object into increasingly bizarre configurations. Like a cosmic sculpture etched by starlight, the warming ice reshaped itself as it journeyed deeper into our solar system. This process can transform an ordinary spherical object into elongated, needle-like forms that baffle astronomers. However, even this peculiar explanation faces challenges. The object appears too small and too dim to be composed entirely of ice. Its surface reflects light like rock or metal, rather than the bright, shiny surface expected of an icy body. Its deep red hue suggests a surface long exposed to cosmic radiation. Over millions of years, it slowly altered its chemical composition in ways ice cannot sustain. Some researchers propose the boldest explanation. What if this isn't a natural object? This unusual shape differs from any observed asteroid or comet. Its precise, slender form appears almost engineered. Could it be a fragment of an alien civilization? Perhaps a technological artifact from another star system, built for purposes beyond our imagination. While most scientists remain skeptical, they cannot dismiss the hypothesis. This object challenges every assumption about natural space rocks. Yet its shape is merely the beginning of the mystery. Speed measurements tell a different story, forcing astronomers to question everything they thought they knew about objects in space. This interstellar visitor isn't just moving fast. It's traveling at an astonishing speed, 196,000 miles per hour. Its velocity is nearly 5 times that of typical comets and asteroids in our solar system. To grasp how astonishing this speed is, imagine standing beside a highway where normal traffic flows at 60 miles per hour. Suddenly, a car streaks past at 300 miles per hour. This is the cosmic equivalent witnessed by astronomers. The speed alone proves the object originated from interstellar space. No object could achieve such velocity through natural gravitational interactions alone. Even our fastest spacecraft barely reach 40 miles per second, with multiple planetary gravity assists. This cosmic wanderer cruises at over 50 miles per second, carrying the kinetic energy from its million-year journey between stars. But speed creates its own mysteries in space. When an object moves this fast, relative to our solar system, it experiences effects unseen by slower bodies. Encountering the interstellar medium, the sparse gas and dust filling the space between stars becomes like facing a cosmic headwind. Over millions of years, this drag should have slowed any object traversing it. Yet this visitor maintained astonishing velocity, suggesting it hasn't wandered as long as initially thought. Ballistic analysis reveals another puzzle. When astronomers traced its path back to its origin, they discovered the object did not traverse space in a straight line. Something influenced its course. During its long interstellar journey, perhaps it passed through another star system, its path bent by gravity. Or perhaps it encountered a massive gas cloud drifting through our Milky Way galaxy. Each contained enough material to build thousands of new star systems. Its speed also meant observers had only a limited window to study this cosmic messenger. Unlike asteroids and comets orbiting the sun, which can be observed for months or years, this interstellar visitor was merely passing through. By the time astronomers detected it, it had already passed its closest point to the sun. Now it was fleeing us at astonishing speed. Day after day, telescopes worldwide race against time to gather as much data as possible before this object vanishes forever into the depths of space. Each night's observation is invaluable, and every measurement may reveal crucial clues about the visitor's nature and the star system that launched it on this cosmic journey. The urgency to understand this object has sparked unprecedented international collaboration. Unlike any discovery in astronomy, observatories from Hawaii to Chile to South Africa have trained their instruments on this fleeting target. Radio telescopes listen for any signals that might indicate an artificial origin. Infrared detectors search for thermal signatures that could reveal the object's composition. Yet, even as this unprecedented observational campaign gathers data, the object holds another surprise, awaiting the scientific community, something that would challenge the laws of physics applied to small objects in space. In June 2018, Marco Michel and his team at the European Space Agency announced a discovery that would send shockwaves through the astronomical community. This interstellar visitor did not follow the path predicted by gravity. As telescopes tracked its movement away from the sun, the object deviated from its trajectory, based solely on gravitational calculations. It was accelerating, not dramatically, but measurably and persistently. The deviation was subtle, like a marble rolling down a smooth tabletop, suddenly nudged by an invisible hand. This acceleration equated to a force, akin to someone gently blowing on your cheek. For a cosmic object traveling at astonishing speeds, this represented a significant anomaly. In space, there is no air resistance or friction. Objects follow predictable paths governed solely by gravity. Planets, asteroids, and comets all adhere to these fundamental laws. This visitor clearly operates by its own rules. For astronomers, this presents a profound puzzle. The acceleration is correct and exhibits the characteristic gas release that occurs when comets approach the Sun. Ice on their surfaces directly converts to gas. This process is called sublimation. These escaping gases act like a natural rocket engine, giving the comet a small but measurable thrust, slightly deflecting it from a purely gravitational trajectory. This phenomenon is well understood and has been observed in thousands of comets. But this object showed no signs of releasing gases to produce cometary acceleration. There was no visible coma. The bright, hazy cloud of gas and dust that surrounds active comets. No tail emanates from the object, because gas and dust particles are pushed away by solar radiation. The telescope sees only a dark object, apparently solid, tumbling through space. Yet somehow, it accelerates like a typical comet. The mystery deepens when astronomers calculate how much gas must be released to produce the observed acceleration. For an ordinary comet, the ejected mass would show clear signs of activity. The object should be surrounded by a bright coma spanning thousands of miles. It should have a spectacular tail, visible even to amateur astronomers with small telescopes. Instead, even the most sensitive instruments failed to detect any trace of such activity. This led to increasingly bizarre explanations. Perhaps the object is ejecting material too faint to see, such as pure carbon particles, which reflect no light. Perhaps it is emitting gas in a narrow jet, pointed directly toward Earth, rendering the ejected gas invisible to our telescopes. Some scientists propose the acceleration stems from the pressure of sunlight itself, acting upon an extremely lightweight object. The light pressure theory requires this visitor to possess a foam-like density, or a shape resembling a solar sail. When light reflects off a surface, photons carry momentum, which can provide a tiny thrust. For most space objects, this radiation pressure is negligible compared to gravity. But for objects with the right combination of size, shape, and density, sunlight can deliver measurable acceleration. This interpretation has sparked the most controversial theory about the cosmic wanderer's nature, a proposal that will divide the scientific community and capture the public's imagination worldwide. The discovery of the first interstellar visitor reveals an alarming truth. NASA scientists have suspected for decades that we are essentially blind to small celestial bodies approaching Earth from deep space. While existing sky survey projects like Pan-STARRS excel at detecting large asteroids, providing months or years of warning before potential impacts, they were designed to detect massive threats from afar. What about smaller objects? Perhaps only hundreds of feet wide. They could appear suddenly, giving us mere days or weeks of warning. The 2013 Chelyabinsk meteor event exposed this vulnerability. A roughly 60-foot diameter object exploded over Russia, with a force equivalent to 30 Hiroshima atomic bombs, injuring over 1,000 people and damaging thousands of buildings. Despite all our sky surveying programs, this cosmic projectile arrived completely undetected because it approached from the direction of the sun, a blind spot beyond the reach of telescopes. Larry De Niro of the University of Hawaii and his team realized that defending Earth requires a fundamentally different approach. Rather than searching for distant, large objects, they needed to build a system capable of scanning the entire visible sky every night. searching for any object moving against the stellar background. This system would be optimized to detect smaller threats that could appear suddenly, leaving humanity critical days or weeks to respond. Thus, the Atlas project was born, the Terrestrial Impact Last Alert System, a name that perfectly encapsulates its mission. This would be our final early warning system, the last alert before impact, for objects too small or too close for other sky survey systems to detect. Atlas was designed to spot a 60-foot asteroid days before impact and a 300-foot asteroid weeks before impact. The engineering challenge was immense. Scanning the entire sky every night required telescopes with an extremely wide field of view and an extremely sensitive camera. Each Atlas telescope must capture a swath of sky 100 times larger than the full moon in a single exposure. The camera must detect objects so faint they are 100,000 times dimmer than the faintest star visible to the human eye. NASA funded the project with $5 million in 2013, recognizing that planetary defense requires this new capability. The first 2 telescopes were built in Hawaii, at observatories on Haleakala Volcano and Mauna Kea Volcano, about 100 miles apart. This separation provides redundancy against weather impacts and enables parallax measurements to quickly determine distances to newly discovered celestial bodies. By 2017, both Hawaiian telescopes were fully operational, scanning the northern hemisphere sky on every clear night. Automated systems capture over 250 gigabytes of data nightly. Computers analyze each image in real time, identifying moving objects. The system processes data equivalent to the entire text of Wikipedia nightly, searching for faint traces of cosmic wanderers. But the Hawaiian telescopes could only observe the northern hemisphere, leaving the southern hemisphere largely unmonitored. NASA recognized this limitation and funded 2 additional telescopes for the southern hemisphere. These new eyes would soon uncover a discovery so mysterious it dwarfed even the first interstellar visitor. By early 2022, humanity achieved an unprecedented feat in our history of observing the cosmos. 4 identical robotic telescopes, spanning thousands of miles across Earth, began operating as a single planetary defense system. The 2 original Atlas sites in Hawaii joined a new facility in South Africa and a site in Chile to create the first sky survey system capable of monitoring the entire dark sky every 24 hours. Each telescope in this global network represents a marvel of astronomical engineering. Their optical systems capture light using mirrors just 20 inches wide, smaller than many amateur telescopes. But what they lack in size, they make up for in field of view. Each telescope images an area of 7.4 square degrees, equivalent to the span of 15 full moons side by side. This vast field of view enables each site to capture a quarter of the entire sky overnight. Cameras attached to these telescopes contain 110 million pixels, capturing intricate details of the vast cosmos with every exposure. For example, if you printed an Atlas image at normal photo resolution, it would cover an entire basketball court. Every night, the data collected by the 4 telescopes combined is sufficient to fill the storage capacity of 50 high-end smartphones. The global distribution of these robotic sentinels creates overlapping coverage, ensuring no blind spots. When it is daytime in Hawaii, the telescopes in South Africa and Chile continue observations. When storms or volcanic smoke affect one location, others maintain vigil. The 120-degree longitude spacing between sites means an asteroid visible for only a day or 2 cannot slip undetected. Each telescope follows the same precise procedure every clear night. The system divides the visible sky into 1,500 distinct regions. Like a cosmic chessboard, the telescope takes 4 exposures of each region, each lasting 30 seconds, spaced 10 minutes apart. This enables the computer system to identify any object moving between images. distinguishing asteroids from cosmic rays, satellites, and distant quasars. Data processing occurs in real time at each site. Powerful computers analyze every image immediately after capture, identifying moving objects and calculating preliminary orbits. The system automatically compares each discovery against databases of known asteroids and comets, flagging only genuinely new objects requiring human attention. Confirmation occurs within hours of discovery. New celestial bodies are reported to the Minor Planet Center, the international clearinghouse for comet and asteroid discoveries. This automated detection system has revolutionized our ability to identify cosmic threats. Since its launch, Atlas has discovered over 700 near-Earth asteroids and 66 comets. The system has successfully detected 2 extremely small asteroids that actually struck Earth, providing crucial validation of its threat detection capabilities. Yet Atlas's capabilities extend far beyond planetary defense. As a byproduct of its multiple nightly scans of the entire sky, the system has become one of the most prolific sky surveys for discovering supernovae, variable stars, and other cosmic phenomena. In July 2025, this global network will make a discovery that will reshape our understanding of visitors from other star systems. July 2025. Like many nights before at Atlas's Chilean site, the robotic telescope at Cerro Tololo Inter-American Observatory, perched high in the Andes, commenced its systematic scan of the southern sky. As the sun set, automated systems powered the sensitive cameras, initiating the nightly ritual of capturing the cosmos one region at a time. Computer algorithms processed each image within minutes, searching for compelling signs of movement against the stellar backdrop, revealing the presence of asteroids or comets. At first, this discovery seemed routine. The detection software flagged a faint object slowly traversing the star field, a typical characteristic of distant asteroids frequently found by Atlas. Preliminary calculations suggested an unremarkable space rock, tracking a normal orbit around the Sun. The automated system dutifully logged the discovery and prepared to scan the next patch of sky. But as additional images accumulated throughout the night, something unusual began to emerge from the data. This object did not follow the elliptical path typical of solar system bodies. Instead, its trajectory exhibited distinct hyperbolic orbital characteristics, identical to the path followed by that enigmatic first interstellar visitor a decade prior. This new object moved too swiftly to be bound by the sun's gravitational pull. The discovery immediately alerted astronomers worldwide. Within hours, telescopes across multiple nations switched their focus to the object's position, racing against time to gather observational data before it vanished into the depths of space. The Gemini North Telescope in Hawaii, the Canada-France-Hawaii Telescope on Mauna Kea, and the Lowell Discovery Telescope in Arizona all joined the observation effort. Unlike the first interstellar visitor, this new object almost immediately revealed its nature. Through their telescopes, astronomers observed a faint, diffuse halo surrounding a bright central nucleus, a clear indication of a coma. Unlike the first visitor, which was a dark, inert rock, this was an active comet, possessing a luminous cloud of gas and dust, spanning the solar system. The coma signaled that this interstellar wanderer was shedding material as it approached the sun. Just like ordinary comets, ice on its surface was sublimating into space, creating the beautiful spectacle that has captivated humanity throughout history. But this comet carries chemical signatures from another star system, offering an unprecedented opportunity to study the composition of material formed around distant stars. Veteran comet hunters David Jewett and Jane Liu confirmed the activity using the Nordic Optical Telescope. Their observations show a clearly visible coma that continues to expand as the object approaches the sun. This marks the first time astronomers have observed an active comet from another star system. performing the same cosmic dance our own comets have followed for billions of years. News of this discovery has sparked a wave of excitement throughout the astronomical community. Unlike the enigmatic first visitor, this new object promises to reveal its secrets through easily understood processes. Spectral analysis could determine the composition of its nucleus. Imaging of the coma could track how its activity evolves as it approaches the sun. Yet excitement carries a sense of urgency, for this cosmic messenger will not linger. Near our home, the official announcement came on July 2nd. Excitement rippled through observatories and space agencies worldwide. The Minor Planet Center, the international body tracking asteroids and comets, released the historic designation. The object was designated C/2025N1 and formally granted the interstellar designation 3I, making it the third confirmed interstellar object in history. The first was the mysterious, elongated visitor of 2017. The second was Comet Borisov, which behaved like a typical comet but originated from interstellar space in 2019. This new discovery represents an unprecedented situation. For the first time, astronomers detected an active interstellar comet while it was still approaching the Sun, rather than after it had begun departing our solar system. This temporal advantage means observers will have months to study the object, as its activity increases, rather than racing against time in desperation. As with previously observed visitors, pre-discovery observations quickly surfaced from telescope archives worldwide. The Vera Rubin Observatory had actually captured the object during its scientific validation observations in June. Though these images weren't processed until after the Atlas discovery, NASA's Transiting Exoplanet Survey satellite, TESS, had even spotted the comet earlier in May, when it was still 6 times farther from the Sun than Earth. These archival observations reveal that this interstellar comet began its activity much earlier than anyone anticipated, long before it reached a distance from the Sun where water ice should remain frozen solid. This suggests its activity is driven by volatile substances like carbon monoxide or carbon dioxide, which can sublimate at lower temperatures. Orbital analysis confirmed what astronomers had suspected from the initial observations. When tracing the comet's trajectory back in time, it clearly originated from beyond our solar system, approaching from the direction of Sagittarius, where the dense stellar bulge at our Milky Way's center lies. This object had traveled for millions of years before encountering the Sun's gravity. Unlike the first mysterious visitor, this new interstellar comet leaves no doubt about its acceleration. Its growing coma and emerging tail perfectly explain its motion through well-understood physics. As ice sublimates from the nucleus, escaping gases provide a natural rocket effect that subtly alters the comet's orbit. No exotic substances or controversial theories are required. This discovery also validates the design philosophy of the global Atlas network. By scanning the entire sky nightly, the system detected this visitor while it remained sufficiently distant from the Sun, enabling extensive observation. Early detection systems focused on spotting large threats months in advance might have missed this smaller object approaching from the southern sky. Within days of its announcement, the Hubble Space Telescope captured the first images of this interstellar visitor, revealing details of its coma structure and composition. These observations will unlock secrets of a journey through interstellar space spanning millions of years. The first detailed image from the Hubble Space Telescope reveals a sight never before captured in human history, an active comet from another star system, displaying the same beautiful phenomenon that has inspired countless sky observers for millennia. The coma extends over 8,000 miles, a luminous cloud of gas and dust, rendering the tiny nucleus visible as it traverses the vastness of space. Spectral analysis reveals familiar signatures: water vapor, carbon monoxide, and carbon dioxide, substances that power comets born within our solar system. Yet this cosmic visitor bears subtle differences, revealing its extraterrestrial origin. Dust particles within the coma are on average larger than those commonly found in solar system comets. Measurements show smaller dust particles, with radii around 1 micrometer, are ejected at speeds of 72 feet per second, while larger particles, 100 times in diameter, move much slower at approximately 6.5 feet per second. These dust characteristics tell us that this comet likely formed in a different stellar environment, on the outer reaches of that planetary system, where distinct temperatures and chemical conditions created ice mixtures unlike those in our solar system. The larger dust particles suggest its parent star system may have had more heavy elements available during planetary and cometary formation. As July transitions into August, telescopes track the steadily growing coma as this interstellar visitor continues its approach toward the Sun. Images from the Canada-France-Hawaii telescope reveal a faint tail beginning to emerge. This is a classic slender feature, pointing away from the Sun, as the solar wind pushes the comet's atmosphere into space. This marks the first time astronomers have observed an interstellar comet develop its full active tail, which carries vital information about the comet's composition and the solar wind conditions it experienced. Unlike the invisible hydrogen gas that may propel the first mysterious visitor, this comet's tail contains easily detectable dust and gases, revealing their chemical composition through spectroscopy. Each element and molecule leaves a unique fingerprint in the light it reflects or emits. Ground-based telescopes worldwide joined the observation effort, creating an unprecedented international collaboration to study this celestial messenger. The Gran Telescopio Canarias, one of the world's largest optical telescopes, determined the comet's nucleus rotates once every 16.75 hours. This rotation rate is typical for small comets, indicating that despite its interstellar journey, the object retains fundamental physical characteristics of its birth environment. The European Southern Observatory contributed by monitoring changes in the comet's brightness. As different sections of its nucleus rotated into sunlight, these brightness variations diminish over time, suggesting that as the comet approaches the Sun, its nucleus becomes increasingly active, with more frozen regions warming and beginning to release gases. Unlike the enigmatic first interstellar visitor, this new cosmic wanderer behaves precisely as astronomers would expect for an active comet. Each observation confirms it follows the same physical laws governing comets throughout our solar system. Yet its normal behavior carries profound significance, deepening our understanding of planetary system formation in the Milky Way. The size disparity between the two interstellar visitors reveals how much we missed in our first encounter. Though astronomers never determined the first slender visitor's exact dimensions, estimates suggest its length ranged from 300 to 3,000 feet. Imagine a colossal skyscraper tumbling through space, perhaps as tall as the Eiffel Tower but stretched into a cosmic needle. That object was already at the limits of telescope detection as it departed our solar system. This new interstellar comet dwarfs its predecessor. Early estimates suggest its nucleus spans several miles in diameter. Rough calculations indicate it is roughly 100 times larger than the first visitor. To illustrate, imagine comparing a school bus to a small city. This size disparity directly translates to observational opportunities, providing astronomers with more material to study and analyze. The larger dimensions explain why this comet could produce such a spectacular display of activity, with more surface area exposed to solar heating and more ice available for sublimation, enabling the comet to generate a bright coma and tail, visible to telescopes worldwide. The first interstellar visitor, however, was simply too small, even with ice inside, to produce detectable gas releases. Size also determines how long an object remains observable. The first interstellar traveler vanished within months of discovery, becoming too faint to track even with the largest telescopes. This new comet, with its massive nucleus and active coma, will remain visible to ground-based telescopes for months, enabling extensive study of its composition and behavior. Mass differences influence how the two objects respond to solar radiation pressure. The first visitor's small size made it susceptible to forces that barely affect larger bodies. Sunlight pressure, magnetic fields, and even solar wind could alter its trajectory in measurable ways. The much more massive new comet follows a more predictable path, primarily governed by gravity. The immense size of this interstellar comet also provides crucial information about the planetary system that ejected it into space. Large comets require substantial amounts of ice and dust to form, suggesting they originate from systems possessing massive debris disks during planet formation. The existence of such large interstellar objects indicates that planetary systems capable of forming large comet populations, which may be common throughout the Milky Way. Furthermore, size influences how cosmic radiation affects objects during interstellar travel. Larger bodies retain more primordial material internally, unaffected by cosmic rays that gradually alter surface substances. This preservation means spectral studies of this comet could reveal relatively uncontaminated sample material from its birth environment. The dramatic size difference between our two interstellar visitors also raises intriguing questions about selection effects. Are we observing a representative sample of interstellar objects, or merely the tip of a cosmic iceberg? When Atlas first detected this interstellar comet, it was traveling at 137,000 miles per hour relative to our solar system. This velocity equates to 38 miles per second, fast enough to cross the entire United States in under 2.5 minutes. To grasp this cosmic speed, imagine standing beside a highway, with cars traveling at 70 miles per hour. This interstellar visitor would flash by 2,000 times faster than the highway traffic, covering the distance from New York to Los Angeles in the time it takes to brew a cup of coffee. But speed in space behaves differently than on Earth. As the comet plunges into the sun's gravitational well, it accelerates dramatically, much like a marble speeding down a ramp. This cosmic wanderer gains momentum as it nears the sun. When it reaches its closest point in October, the comet will be traveling at over 160,000 miles per hour. This acceleration demonstrates the immense power of our star's gravity. The sun's gravitational pull spans billions of miles of space, gently tugging at this interstellar visitor and bending its path from a straight line into a graceful hyperbola. The comet arrived from interstellar space along a nearly straight trajectory, but the sun's influence gradually alters its path until it swings around our star. Like a cosmic slingshot, its extreme velocity presents challenges rarely encountered by astronomers studying normal solar system bodies. Most comets and asteroids move relatively slowly across the sky, allowing telescopes to track them for hours or days with the same instrument settings. This interstellar speedster races through a telescope's field of view. Observers must constantly adjust their pointing and tracking to keep the target centered. Telescopes designed for tracking slow, predictable stellar motion struggle to keep pace with this cosmic sprinter. The object moves so rapidly that exposure times must be meticulously calculated to prevent streaking across the detector during long observations. Astronomers must balance the need for long exposures to gather faint light with motion that could blur the image. Its high velocity also drastically compresses the observation window. Unlike periodic comets that return every few years or decades, offering multiple study opportunities, this visitor will pass through our solar system only once. It will depart with its secrets, returning to the depths of interstellar space, never to return to our vicinity. The velocity difference between our solar system and this interstellar traveler reveals profound insights into galactic motion. Our entire solar system orbits the galactic center at 500,000 miles per hour. But this comet originates from another part of the galaxy, carrying its own orbital velocity. The collision of these two cosmic reference frames generates the relative motion that makes interstellar objects so unique. Understanding these velocities helps astronomers trace celestial bodies back to their possible origins and project forward to their future destinations. After its fleeting encounter with our Sun, this cosmic messenger will continue its journey into the vast, dark expanse between stars. Every photon reflected from this interstellar comet carries information gathered over millions of years traversing the Milky Way. When astronomers point their spectrometers at the glowing coma, they are essentially conducting chemical experiments on matter formed around distant stars. Each element and molecule absorbs and emits light at specific wavelengths, creating a unique fingerprint revealing the composition of gas and dust flowing from the nucleus. These spectral features act like cosmic DNA, carrying the genetic code of another planetary system. Initial spectral observations revealed both familiar and surprising elements within the comet's coma. Water vapor was immediately confirmed, verifying that H2O ice formed around other stars just as it did in our solar system. Carbon monoxide and carbon dioxide appeared in expected proportions, indicating the fundamental chemistry producing comets operates similarly across different stellar environments. Yet subtle variations in isotope ratios tell a more complex story. Isotopes are variants of the same element differing in the number of neutrons within their atomic nuclei. For instance, billions of years ago during comet formation, the ratio of different oxygen isotopes depended on the specific conditions of temperature, pressure, and available material within the primordial nebula. The deuterium to hydrogen ratio in water vapor provides particularly valuable information. Deuterium is heavy hydrogen, containing one proton and one neutron instead of just a single proton. The amount of deuterium incorporated into water ice depends on the temperature and density conditions during formation. By measuring this ratio, astronomers can estimate whether a comet formed in the warm inner regions of its protoplanetary disk or in the cold outer reaches where most comets are born. Early measurements indicate this interstellar visitor formed under conditions similar to those found in our solar system's outer regions. Its chemical signature most closely matches comets originating from Neptune-distant icy reservoirs in our own Kuiper belt. This similarity suggests fundamental planet-forming processes may be remarkably consistent across different stellar systems. However, some trace elements show intriguing deviations from solar system norms. The relative abundance of certain metals in the comet's dust particles suggests its parent star had a composition slightly different from our Sun. The gas clouds that form stars are enriched with heavy elements produced by the explosions of previous generations of stars, and these differences are incorporated into the planets and comets that form around them. The organic compounds detected in the comet's coma raise the most intriguing possibilities. Simple carbon-based molecules like formaldehyde and methanol are common in solar system comets. But this interstellar visitor may carry more complex organic chemistry. Advanced spectroscopic techniques can identify molecular structures, revealing the chemical evolution occurring in their birth environments. These chemical signatures provide our first direct material sample from another planetary system, offering insights otherwise accessible only through interstellar travel. Yet this cosmic visitor story tells a more detailed tale about its distant home environment. The elegant tales streaming from this interstellar comet are more than a beautiful celestial spectacle. They are a time machine carrying messages from another star system. As solar wind pushes gas and dust away from the comet's nucleus, it creates two distinct types of tales revealing different aspects of the object's composition and history. The ion tail, composed of charged gas molecules, points directly away from the Sun like a cosmic wind vane. The dust tail forms along a slightly curved path, shaped by the balance between solar radiation pressure and the comet's orbital motion. The ion tail provides a real-time chemical analysis of gases released from the nucleus. Ultraviolet radiation from the sun strips electrons from gas molecules, producing ions that glow at characteristic wavelengths. Sodium ions emit yellow light, carbon monoxide ions appear blue, and water ions produce a distinctive blue-green glow. This natural spectrum reveals not only which elements are present, but also their relative abundances. Dust tails tell different stories about the solid material within comets at their formation. Microscopic analysis of light scattered by dust particles reveals their size distribution, composition, and structure. Unlike gas molecules, which may be altered by chemical reactions during a comet's journey through space, dust particles more directly record conditions within the primordial nebula. The ratio of gas to dust production rates indicates how comets formed and evolved within their birth environment. Comets formed near their parent star tend to have lower ice content and produce relatively less gas compared to dust. Comets formed in the cold outer regions of planetary systems typically contain higher ice content and produce spectacular gas tails when approaching their stars. Preliminary observations indicate that this interstellar comet's gas-to-dust ratio resembles that of long-period comets originating from our solar system's Oort cloud. This similarity suggests the visitor formed in the cold outer reaches of its protoplanetary disk, where temperatures were low enough for volatile ices to condense and accumulate on solid particles. The dust story also reveals information about the magnetic field environment surrounding the comet's parent star. During planetary system formation, varying stellar magnetic field strengths influence how dust particles aggregate and grow into larger bodies. The size distribution of dust particles in the tail bears the signature of these ancient magnetic processes. As the comet continues its approach toward the sun, the tail will grow longer and more spectacular. Increased solar heating will cause ice deep within the nucleus to sublimate, potentially exposing material frozen since the comet's formation billions of years ago. This primordial material may contain organic molecules or mineral structures, offering direct evidence of chemical conditions in another star system. The tail's evolution over time also constrains models of how comets change during millions of years of interstellar travel. Cosmic radiation gradually alters surface material, but the interior remains largely unchanged. As solar heat penetrates deeper into the nucleus, astronomers can essentially peel back layers of time, studying materials representing different eras of the comet's history. The ability to study an active interstellar comet represents an unprecedented opportunity in planetary science. For the first time, we can track these dynamic processes in real time on an object originating from another star. Tracking an interstellar comet streaking across the sky pushes telescope technology to its absolute limits. The fastest military sniper bullets travel at approximately 3,000 feet per second. This interstellar comet moves at 200,000 feet per second, roughly 67 times faster than a bullet. But unlike a bullet traveling in a straight line for seconds, this cosmic projectile traverses the sky along a curved path for months. It requires continuous adjustments to keep it in view. Modern telescopes employ sophisticated computer-controlled systems to track moving objects. The telescope mount calculates the object's predicted position thousands of times per second, making minute adjustments to compensate for Earth's rotation and the target's motion through space. For most asteroids and comets, this tracking is routine. For interstellar objects, it pushes these systems to their engineering limits. The challenge begins with pinpointing the comet's exact location from one night to the next. Normal solar system bodies follow predictable elliptical orbits that astronomers can calculate years in advance. Interstellar objects follow hyperbolic trajectories that are harder to predict, especially when gas emissions from the nucleus slightly alter the orbit. Professional observatories worldwide coordinate their observations to maximize coverage. As the comet traverses different parts of the sky, when it dips below one observatory's horizon, telescopes on the other side of the Earth take over monitoring. This global relay ensures continuous monitoring despite Earth's rotation. The comet's rapid motion requires advanced imaging techniques to extract maximum information from each observation. A single long exposure would result in streaks as the comet moves. Astronomers capture a series of shorter images that can be mathematically combined to enhance faint details. This processing technique, called shift and stacking, keeps the comet sharp while blurring background stars into streaks. State-of-the-art observatories can track moving objects with such precision that they maintain targets in view for hours at interstellar speeds. The Hubble Space Telescope, operating above atmospheric distortion, obtains some of the sharpest images ever acquired of an interstellar object using this advanced tracking capability. Radio telescopes face greater challenges when attempting to study interstellar visitors. Radio observations require extremely precise pointing, often accurate to fractions of an arcsecond. The combination of the object's motion and Earth's rotation means radio telescopes must constantly adjust their pointing while maintaining precise frequency tuning to detect faint signals. The Doppler effect adds another layer of complexity to radio observations. As the comet approaches or recedes from Earth at tens of miles per second, it can alter the frequency of any radio signal sufficiently to overwhelm the narrow frequency bands used by sensitive radio receivers. Astronomers must continually adjust their receiver frequencies to compensate for cosmic Doppler shifts. Despite these challenges, the global astronomical community has developed unprecedented coordination in tracking this interstellar visitor. Ground-based telescopes, space-based observatories, and even amateur astronomers have contributed to a comprehensive understanding of the comet's behavior and composition. This coordinated effort will culminate when the comet reaches perihelion, its closest point to the Sun, in late October. October 2025 will mark the most dramatic moment in this interstellar comet's billion-year journey. On that day, the cosmic wanderer will reach its closest distance to our Sun, 130 million miles. This will position it just inside Mars' orbit, close enough to the Sun's intense radiation to drive spectacular activity within the comet's nucleus. By comparison, this distance is approximately 40% closer than Earth's average distance from the Sun, subjecting the comet to nearly 3 times the solar heating intensity experienced by our planet. The perihelion passage will transform this already active comet into a cosmic spectacle. As solar heat penetrates deep into the nucleus, it will sublimate ice that has remained frozen since the comet formed billions of years ago around another star. This untouched ice, preserved throughout its long interstellar journey, may contain primordial material revealing the original chemistry of the comet's birth environment. The heightened activity will cause the comet's tail to grow exceptionally long and bright. Models predict the tail could stretch millions of miles, potentially making it visible to amateur astronomers with modest telescopes. Despite the comet's great distance from Earth, this spectacle will offer a rare opportunity for citizen scientists to contribute observations of an object originating from another solar system. However, intense solar heating also presents observational challenges. As the comet approaches perihelion, its position in Earth's sky moves closer to the Sun, making it increasingly difficult to observe from the ground. The brilliant solar glare will eventually overwhelm the comet's light, forcing astronomers to suspend observations until the object reappears on the far side of the Sun in early December. This solar conjunction represents a critical gap in observational coverage occurring precisely during the comet's most active phase. Space-based observatories designed to study the solar corona, such as the Solar and Heliospheric Observatory, SOHO, may be able to capture images of the comet during this close passage. These specialized instruments can block the solar disk while observing the surrounding space the comet will traverse. The gravitational effects of the Sun's proximity will also most significantly bend the comet's orbit. The perihelion passage, bringing this visitor from interstellar space, will be influenced by the sun's gravity, potentially altering the comet's future path through the Milky Way. Precise measurements of the comet's position during this phase will help astronomers predict its destination after leaving our solar system. Extreme solar heating may also reveal information about the comet's nucleus structure. If the nucleus contains significant amounts of more volatile ices like carbon monoxide or nitrogen, they could undergo explosive sublimation near perihelion. This might fracture the nucleus or create dramatic bursts of activity. Such events would provide unique insights into the internal structure and composition of this interstellar visitor. For planetary scientists, the perihelion passage represents an opportunity to study how material from another solar system reacts to solar radiation. Whether this comet behaves similarly or differently to solar system comets may reveal fundamental differences in composition or structure reflecting distinct formation environments. As perihelion approaches, telescopes worldwide will maintain continuous surveillance of this cosmic visitor. Observations gathered during these critical weeks will yield the most detailed portrait ever obtained of an active interstellar object. Unlike comets, whose periodic returns every few years or decades can be predicted, this interstellar visitor makes only a single, permanent pass. This distinction lies in the fundamental nature of its orbit. Most comets within our solar system follow elliptical paths that bring them back into the inner solar system. Halley's Comet returns regularly every 76 years, while Hale-Bopp visits approximately every 2,500 years. These periodic comets are bound by the sun's gravity into an endless cycle that has persisted for millions of years. This interstellar comet follows a hyperbolic trajectory, a mathematical curve that approaches the sun once before diverging into infinity. Imagine throwing a ball against a wall. An elliptical orbit resembles a ball tethered to a rubber band, stretching and contracting, but always returning. A hyperbolic orbit is like a ball hurled with force, bouncing off the wall and flying away forever, never to return. The comet's excessive velocity holds the key to understanding its trajectory. Traveling at 220,000 miles per hour, it carries too much kinetic energy for the sun's gravity to ever capture it. Our star can bend a comet's path and accelerate it during its passage, but it cannot slow the visitor enough to capture it in a closed orbit. The comet will swing around the sun like a cosmic slingshot, returning to the depths of interstellar space. After its perihelion passage, the comet will begin its eternal journey away from our solar system. It will first cross Mars' orbit in early November, then Jupiter's orbit in early 2026. By 2028, it will cross Saturn's orbit and enter the outer reaches of our solar system, where sunlight becomes too faint to drive significant cometary activity. The comet will continue drifting outward for millennia, gradually fading as it recedes from the sun's warming influence. Eventually, it will cross the boundary where solar wind yields to interstellar medium. At this point, roughly a century later, it will formally return to interstellar space, bearing the minute alterations wrought by its fleeting encounter with our sun. During its journey through the solar system, the comet will lose a small fraction of its mass through sublimation. These materials will remain behind, joining the trace amounts of interstellar dust and gas already present in our solar system's inventory. In a sense, our sun will forever hold a tiny sample of matter from another galaxy. Even as the comet's main body escapes back into the Milky Way, its gravitational interaction with the sun will subtly alter the comet's future path through the galaxy. Though minor, this shift means the comet will travel along a different trajectory than it would have without this solar encounter. Over millions of years, such a slight deflection can determine which star system, if any, the comet will next visit. The one-way nature of this encounter makes each observation invaluable. Unlike periodic comets that offer multiple study opportunities centuries or millennia later, astronomers have only one chance to learn everything about this interstellar messenger. Once it departs, human civilization may never see this particular object again. The current observations provide a unique window into another star system. The story of this interstellar messenger is not merely one of serendipitous discovery. It profoundly illuminates our place in the cosmos and the grand picture of intergalactic material exchange. By juxtaposing these two interstellar visitors, we glimpse a universe far richer and more complex than we imagined. Oumuamua and our 2025 comet visitor represent two extremes of interstellar objects. One defies all expectations with its enigmatic nature. The other follows familiar physical laws with predictable regularity. Oumuamua's extreme slenderness, at least 10 times longer than it is wide, rolls through space like a skyscraper lying on its side. This shape is unprecedented in our solar system. Our most elongated asteroids rarely exceed a length-to-width ratio of 3:1. Its dark surface exhibits a deep reddish hue, an ancient imprint of millions of years of cosmic radiation bombardment. Most perplexing is its acceleration, without any visible gas or dust release. This defies our core understanding of cometary behavior. In contrast, our second visitor, C/2025N1, is a textbook active comet. It possesses a classic and spectacular coma and tail. Its chemical composition is clearly revealed through spectral analysis. Its acceleration can be fully explained by the sublimation of ice from its surface, following physical mechanisms we've studied for decades. The difference in size is equally striking. Oumuamua may be only a few hundred meters long, while C/2025N1's nucleus is estimated to be several miles across. This allows the latter to generate and sustain the intense activity we observe. This size disparity also dictates their observable lifetimes. Oumuamua vanished from the field of view of our most powerful telescopes within months of its discovery, while C/2025N1 remained under our continuous study for several months. This contrast raises a critical question. Is Oumuamua a rare anomaly, or the first evidence of widespread diversity among interstellar objects? The discovery of C/2025N1 strongly suggests the latter. The variety of interstellar visitors produced by the cosmos may be as rich as the small bodies within our own solar system, from dark rocks to active ice balls, from elongated fragments to nearly spherical nuclei. Our understanding of interstellar objects is shifting from the wonder of individual cases to the statistics of their population. This diversity points directly to their equally diverse origins. Oumuamua may be a fragment torn from a larger body by tidal forces or collision, perhaps originating from a distant planetary system, whose internal dynamics differ significantly from our own. Its extreme shape may capture the instant of that ancient disruption, while its ancient surface color narrates its long journey through interstellar space. C/2025N1, however, is likely a typical comet, born in the frigid outer reaches of its parent star system, where volatile substances could condense into ice, gently flicked out by the gravity of a passing giant planet, embarking on an eternal interstellar odyssey. Its behavior tells us that, at least on some fundamental level, the process of comet formation in other star systems mirrors that of our own solar system. These distinct origin stories suggest the existence of diverse planetary system architectures throughout the Milky Way. Some systems may have undergone violent dynamical perturbations, producing abundant debris like Oumuamua, while others may resemble our solar system, possessing a stable outer comet belt, occasionally contributing visitors to interstellar space. Statistical analysis of these interstellar objects' trajectories can even help us map the galactic gravitational environment. Their paths through the interstellar medium are influenced by the gravitational fields of stars and dark matter along their route. Though this influence is minuscule, collecting a sufficient sample size might allow us to decipher secrets about the distribution of matter in the Milky Way. Chemical analysis of these interstellar visitors provides us with a novel tool for studying exoplanetary systems. Prior to this, our only method for studying exoplanets was through indirect analysis of their host star's light, measuring tiny stellar wobbles or changes in starlight filtered by planetary atmospheres. These methods, while powerful, yield limited information. Now, interstellar objects deliver pristine material from other stellar systems directly to our doorstep. The spectrum of C/2025N1 is like a chemical report card from its birthplace. It reveals water ice is ubiquitous throughout the Milky Way. Carbon monoxide and carbon dioxide are also common comet constituents. These findings support the notion that the fundamental chemical ingredients necessary for life may be widely distributed throughout the cosmos. Even more exciting is the composition of the dust particles within it. Larger particle sizes suggest its parent star system may be rich in heavy elements. These elements were produced by previous generations of stars and dispersed into the interstellar medium through supernova explosions. Thus, studying the composition of interstellar objects is not merely examining individual planetary systems, but also investigating the local chemical evolutionary history of our Milky Way. These cosmic messengers essentially facilitate large-scale material exchange across the Milky Way. When a planetary system ejects an asteroid or comet into interstellar space, it contributes its chemical signature to the galactic community. This material may be captured by another planetary system millions of years later, or even delivered to a habitable planet. This process, termed galactic seeding, implies that no world is truly isolated. We are all part of this vast cosmic exchange network. Such material exchange may hold profound significance for the origin of life. Panspermia theory posits that the seeds of life could have spread between planets or even star systems via comets or asteroids. While we have yet to find evidence of life on any interstellar object, they do carry complex organic molecules essential for life. If the building blocks of life can survive and travel through interstellar space, then life itself may be far more common in the Milky Way than we imagined. The discoveries of Oumuamua and C/2025N1 have fundamentally altered our understanding of the solar system's place in the cosmos. We once believed the solar system to be a relatively closed system, occasionally disturbed by external influences, but largely self-contained. We now know the solar system is an environment open to interstellar visitors who constantly traverse our space. Some, like Oumuamua, are merely fleeting passers-by. Others, like C/2025N1, put on a brief yet spectacular show. This shift in understanding resembles a modern-day version of the Copernican revolution in human history. We not only recognize that Earth is not the center of the universe, but now realize our solar system is not an island either. We are part of vast interstellar flows of matter and energy. This new perspective also holds implications for our search for extraterrestrial life. If matter can be exchanged between stellar systems, then the building blocks of life, or life itself, might also be exchanged. This implies life may not have originated independently on one world and then spread, but could have co-evolved across the scale of the entire galaxy. Biological innovations on one world could be shared with others through this cosmic exchange network. Though this may sound like science fiction, the existence of interstellar objects makes it physically possible, even if life itself hasn't spread this way. The building blocks of life, complex organic molecules, are almost certainly being dispersed. Our study of interstellar objects remains in its infancy, yet the pace of technological advancement is astonishing. Next-generation sky survey instruments like the Vera Rubin Observatory are about to come online. It will scan the heavens more deeply and frequently than any existing system. Astronomers predict it could discover several, even dozens, of interstellar objects annually. We will shift from studying rare curiosities to examining a population. This will enable us to answer fundamental questions about their distribution and nature within the Milky Way. We might even discover clusters of interstellar objects originating from very specific directions. This could point to a common source, a star system that recently experienced a dynamical disturbance, ejecting its internal material into the galaxy. Perhaps the most exciting prospect is dispatching spacecraft to visit these interstellar visitors. The Comet Interceptor mission concept under study by the European Space Agency is designed for rapid launch upon discovery of a suitable target. If we detect an interstellar object sufficiently early, we could potentially send a probe to rendezvous with it, fly by it, or even land on its surface. Such a mission would be a game changer. It would allow us to conduct in situ measurements, analyze its surface and internal composition, search for organic molecules, and even potential biosignatures. This would mark humanity's first direct encounter with material from another star system. Its scientific value would be immeasurable. It could provide our first direct evidence that other star systems possess all the ingredients necessary for planet and life formation, or it might reveal entirely unfamiliar chemistries, challenging our understanding of planetary formation conditions. Either way, it will profoundly reshape our understanding of our place in the cosmos. From Oumuamua's unexpected visit to the systematic discovery of C/2025 N1, we are witnessing the dawn of a new astronomical era. We have learned to no longer view the solar system as a closed garden, but rather as a bustling crossroads within the Milky Way. Interstellar objects are the travelers on this cosmic highway, each carrying stories of their distant homelands. By deciphering these narratives, we gain insights not only into other star systems, but also into the origins and destiny of our own solar system. After all, our solar system too sends its own messengers into interstellar space. Occasionally a Kuiper Belt object or an Oort cloud comet gains sufficient velocity through gravitational interactions with other bodies to escape the sun's gravitational grasp and become an interstellar object. When it crosses another star system millions of years later, astronomers there may gaze upon it and wonder, what does this tiny fragment from the solar system signify? This cosmic detective story is far from over. In fact, it has only just begun. As we weave ever more powerful nets across the sky, we will capture more messengers from the stars. Each one may reveal new secrets of the universe, inviting us to keep exploring, to keep thinking, and to keep marveling at our true place in the cosmos. A new era of interstellar object discoveries has only just begun. What we currently observe is merely the tiniest tip of the iceberg. Theoretical models predict that at any given moment, between 10,000 and 100,000 interstellar objects traverse the vast expanse of our solar system. The vast majority of these cosmic wanderers remain hidden in the cold, dark depths beyond Neptune's orbit. They are too faint for our current telescopes to detect. But with the arrival of next-generation observatories, this search is about to undergo a revolutionary transformation. The Vera Rubin Observatory is one such game-changing giant. Perched atop Chile's Cerro Pachón mountain, it houses the largest digital camera ever built, a colossal 3-ton, 3.2 billion pixel behemoth. This engineering marvel can capture a swath of sky, equivalent to 40 full moons. Its sensitivity is sufficient to detect objects 100 million times fainter than the dimmest stars visible to the human eye. At Rubin's core lies the Legacy Survey of Space and Time, a decade-long deep survey of the visible sky that will fully map the entire southern hemisphere every 3 nights, creating an unprecedented cosmic movie for the search for interstellar objects. This means we'll move beyond relying on serendipitous discoveries to conducting systematic population censuses. Computer models predict Rubin could discover dozens of interstellar objects annually. We will shift from studying rare curiosities to analyzing an entire population. This new dataset will answer critical questions about the fundamental nature of interstellar objects. How do their sizes distribute? Do their orbital inclinations show directional preferences? Does their total population size match predictions from planetary formation theories? Answers to these questions will provide invaluable insights into the formation and dynamic history of planetary systems within the Milky Way. The Rubin Observatory's unparalleled depth and survey frequency will also enable us to detect smaller, fainter interstellar objects. We may even find cosmic visitors the size of houses or even cars. These tiny fragments, likely debris from collisions within other star systems, will offer unique insights into the internal structures of exoplanetary asteroids and comets. This is research unattainable with larger celestial bodies. Beyond Rubin Observatory, a series of new astronomical facilities are preparing to join this search. The Simons Observatory in Chile's Atacama Desert will scan the entire sky with unprecedented sensitivity for millimeter wave signals. This wavelength is particularly effective for detecting cold, dark objects, like those that have traveled through interstellar space for millions of years. The European Space Agency's Euclid Space Telescope is already measuring the universe's accelerated expansion, but its vast field of view and sensitive infrared detectors will also become powerful tools for spotting faintly moving celestial bodies. These new eyes will collectively create a global, continuous sky monitoring system, ensuring no interstellar visitor can pass through the inner solar system unnoticed. Space-based observatories extend our vision into new dimensions. The James Webb Space Telescope has already demonstrated its transformative capabilities. Its 6.5-meter-wide golden mirror can gather 6 times more light than the Hubble Space Telescope. But its true revolutionary advantage lies in its optimization for infrared band observations. Infrared radiation is the perfect tool for studying cold objects, such as interstellar comets far from the sun's heat. The Webb telescope can detect the thermal radiation from the comet nucleus itself, without relying on reflected sunlight. This enables precise measurements of these visitors' dimensions and surface properties. More significantly, Webb's powerful spectrometer can resolve detailed chemical fingerprints across infrared wavelengths within interstellar comet comas. It detects precise signatures of water and organic molecules, even distinguishing between different types of ice and silicate dust. These measurements will provide our first detailed view of chemical complexity in other star systems. Successors to the Webb telescope are already in the planning stages, such as the proposed Hubble Legacy Telescope, a space observatory with a larger mirror and wider field of view. It will enable more frequent monitoring of interstellar objects and study their evolution over time. These space-based observatories, free from Earth's atmospheric turbulence, can capture exceptionally clear and stable images. This is crucial for detecting tiny satellites orbiting these interstellar visitors, or resolving details on their nucleus surfaces. Discovering these objects is merely the first step. The true holy grail is the ability to study them up close. This is where interstellar interception missions come into play. The European Space Agency has approved the Comet Interceptor mission. It represents a new paradigm in exploration. Unlike traditional space missions, which typically lock onto specific targets years before launch, the Comet Interceptor will be launched into a holding orbit at the Sun-Earth Lagrange point L2, where the gravitational forces of Earth and the Sun are in equilibrium, providing a stable parking spot. Once a suitable interstellar target is identified by telescopes on Earth or in space, the Comet Interceptor will fire its thrusters to depart its holding orbit and rendezvous with this cosmic visitor. The mission comprises a main spacecraft and 2 smaller probes. They will approach the target from different angles, providing a 3-dimensional view of its nucleus, coma, and tail region. Such multi-angle observation is crucial for understanding the structure and composition of these objects. The Comet Interceptor carries an advanced suite of instruments, including a high-resolution camera, dust mass spectrometer, and gas chromatograph. It will be able to map the nucleus's surface, analyze the chemical composition of dust particles, and directly sample gases within the coma. Such a mission could ultimately resolve the mystery surrounding Oumuamua's nature. Should we encounter another similar object, in situ measurements could determine its surface composition, detect any residual outgassing phenomena, and finally determine whether it is a peculiar rock, a hydrogen iceberg, or something we have yet to imagine. For the more distant future, scientists are conceiving even more ambitious mission concepts. One idea involves developing rapid response launch capabilities, storing spacecraft in warehouses, so that once a promising interstellar target is discovered, launch preparations could be completed within weeks or months, rather than the years typically required. Another concept involves pre-deploying interceptors, positioning them in orbits around the Sun, optimized for rapid rendezvous upon discovery of an interstellar object. These missions require advanced propulsion systems, such as solar electric propulsion or even experimental nuclear thermal rockets, to deliver sufficient velocity to catch up with these high-speed travelers. Recent technological advances have made once sci-fi concepts feasible. Lightweight composite materials reduce spacecraft structural mass, allowing greater fuel capacity for orbital maneuvers. AI-driven autonomous navigation systems will enable real-time course adjustments upon target approach, eliminating delays from Earth-based command transmission. Miniaturization enables small CubeSats to carry precision instruments once requiring large spacecraft. Collectively, these advancements make dedicated interstellar missions increasingly feasible. Beyond intercept missions, proposals exist for rendezvous missions, where spacecraft not only fly past targets, but accompany them for months or even years, observing their entire journey from distant solar approach to perihelion passage and departure. Such long-duration missions would provide the complete story of how these objects respond to solar heating, revealing when and where volatiles begin to sublimate, and how their surfaces transform under intense solar radiation. These studies would hold profound scientific significance, offering pristine samples of the formation conditions in other stellar systems. Imagine holding a fragment from an asteroid orbiting another star. We could measure its isotopic ratios. These ratios record the conditions of its parent nebula. We could search for mineralogical features absent on Earth. Such features might point to distinct formation environments. We could even test planetary formation theories by examining how dust grains in these objects coalesced within protoplanetary disks. Studying interstellar objects may also profoundly impact questions about life's origins. We already know comets contain complex organic molecules, the chemical building blocks of life. But do other star systems produce the same or different organic chemistry? Studying organic compounds in interstellar comets could reveal whether the chemical processes needed for life are universal or unique. If we discover amino acids or other prebiotic molecules on objects from another star system, it would strongly suggest life's ingredients are widespread throughout the Milky Way, and perhaps even point to a universal standard for life's chemistry. Beyond scientific returns, studying interstellar objects holds significant practical implications. Developing capabilities to rapidly intercept these high-velocity targets directly enhances our ability to protect Earth from potentially hazardous asteroids. Navigation and control technologies used to track and rendezvous with interstellar objects could be applied to deflect an asteroid discovered on a collision course with Earth. Furthermore, investigating how these objects are affected by cosmic radiation and micrometeoroid impacts during their long interstellar journeys will provide invaluable insights for designing spacecraft for long-duration deep space missions, including potential future interstellar exploration missions. As we look to the future, the possibilities for interstellar object research are limitless. We can envision a global network of automated telescopes, continuously monitoring the sky, with artificial intelligence systems identifying and classifying new visitors in real time. We can envision a fleet of standby interceptors, ready for launch upon discovery of particularly interesting targets. We can envision international collaborative missions, sending spacecraft from multiple space agencies to the same interstellar object for comprehensive study. One of the most exciting aspects of this new frontier is its potential for democratization. As facilities like the Rubin Observatory begin operations, the data they generate will be open to astronomers worldwide, including amateur astronomers and citizen scientists. Anyone can sift through these vast data sets, searching for moving points of light. Perhaps the next interstellar visitor will be discovered by an amateur from their own backyard. This collective effort unites humanity as a whole to explore the mysteries of our cosmic neighbors. From Oumuamua's unexpected arrival to the era of systematic search and interception missions, we've traveled a long road in just a few short years. We once believed our solar system was an isolated outpost. Now we recognize it as part of a vibrant cosmic community, a community constantly visited by travelers from other stars. The messages these interstellar messengers bring are not only about their distant homes, but also about our own place in the universe. By studying them, we are learning how the Milky Way mixes its ingredients, how planetary systems form and evolve, and perhaps even how life itself began. This cosmic detective story is far from over. In fact, it has only just begun. With every new pair of eyes gazing skyward, with every new mind pondering the data, we draw closer to unraveling the mysteries brought by these cosmic wanderers. So stay tuned, keep your curiosity alive, and prepare for the next messenger from the stars, for it may be heading our way at this very moment, carrying a new chapter of the cosmos waiting to be read.